Welcome to Epic Home Tech. This is Jeremy and my co-host Jared.
Hello, hello.
And in this video we're going to go over Juniper Networking. We're going to set up a 4-router setup with replicating a scenario where you've got dual ISPs. You're going to set up BGP peering with your ISPs, and we're going to get some routes exchanged. So we'll have our left and right routers. We'll be separated by our ISP devices and some networks. So let's get into it. I've already got all of our devices started up. So we'll quick run through the basic configurations that we went through in our previous 2 videos, and we'll move right on into getting the BGP set up. Starting on our left, get logged in. Already got our diagram all put together with our numbers. For whatever reason, getting the CLI started takes a lot longer than I did prefer. Alright, edits, load override terminal, system hostname left, hostname root authentication, set a password, which I think I just mistyped. Yes, sir. Alright, commit that so we've got a name. This is ISP1. So we're going to edit, load override terminal. One. Always remember to set your plain text password for your root authentication. I guess it doesn't have to be plain text password. Commit that. This is ISP2. Root authentication. You can set other, you can set other types of passwords. Yeah, I did it again. So plain text password is just what you do if you're going to be mashing it in at the keyboard, but you can also paste in the pre-hashed password secret if you have the ability to generate a shadow password, a hashed password. Or you're going to copy it from another device. Do make sure though that it is a Juniper device that you're copying from, or a Linux device. I don't believe you can copy a Cisco hashed password into a Juniper device. System plain text password. All right, now everybody's got a name. All right, so we're going to set interfaces, Ethernet, not Ethernet, interfaces, GE000.0. We'll set a description. SP1. And unit 0. Family inets. Address. And if we look at our diagram, we've got 10.1.1.2 and it's a /30. And we're going to go ahead and get our other interface set up as well. So 001, description, ISP2, interfaces GE001, unit 0, family inet, address, 10.2.2.2/30. Alright, so we got to put these in security zones. We're going to go ahead and set security zone, and we're going to create separate zones for each of the interfaces and the ISPs. So ISP1, we're going to do host inbound traffic, we're going to do system services, and we're just going to do ping so that we can troubleshoot it later. 0.1, and we're going to go ahead and we're going to go to security zones, and we see our security zone, and we're just going to go ahead and we're going to copy security zone ISP1 to security zone ISP2. We're going to delete security zone ISP2 interface, and we're going to set security zone ISP2 interfaces GE0011. There we go. Now we've got our 2.
Perfect.
I don't think we need any policies, so let's go ahead and commit that. All right, moving on.
One thing that you did there that's I always thought, I mean, I never did it until I started doing a bunch of different devices, but the actually giving a description to the interface, because you hand this thing off to somebody, you know, I mean, you get a diagram or whatever, if they log in, they can actually tell what that port is supposed to be. I never did it for a long time, but now it's kind of like one of my, I don't want to say one of my favorite things to do, but very useful tool.
And you can see the descriptions as well. If you go show interfaces descriptions, well, you would if you had interfaces. Ha! So I botched that one up, didn't I? So if we go top show interfaces, I don't have a unit 1 in either of those, do I? All right, so let's go ahead and fix that. The security zone. So you could have a unit 1 if you're going to be setting up VLANs or some other specific protocol scenarios, but we obviously do not have those because we don't need those. So let's go ahead and assign the appropriate interface. Interface is GE000.0, and let's go ahead and fix the other one because it will complain the same. So security zone ISP2 interfaces 0010. And we'll just do a commit check just to make sure we got that right. And you see my CPU is cranked up. Let's see what we got here. Hell, here's my CPU. We're at 70% used already. I've only got 6.5 idle. Still got plenty of memory though, so we're good there. All right, I've check succeeded. Moving on. All right, so set interfaces. Hold on one second. Gotta fix my submix. Music was a little loud in my ear. All right, 00. And description. And we're gonna call this left. Sometimes it's better to have your descriptions a little bit more specific, direct than clever. So we'll just stick to something simple. Unit 0 family iNet because we're doing IPv4 address and we're 10.1.1.30. And let's go ahead and set our other interface GE01 description right. And we arrow up. Unit 0 family iNet address and 33130. And we're going to create one security zone. And we're just going to call this, we'll just call it WAN. Host inbound traffic, system services ping. And interfaces 0000 and 10. And we'll commit check. Let's go over here. Set interfaces 000 description left. Yeah, okay. Only inet address, and we are 10.22.1.30. Interfaces G01 description right, and unit 0 family inet address. No, not 2's. 4.1.30. Set security zone WAN, host inbound traffic, system services ping. Interfaces 000.0 and 1. Commit that. Alright, now we're over to write. GE00 description ISP1 unit 0 family inet address 33230. Set interfaces 01 description ISP2. inet address 10.4.4.2.30. So I'm missing. Oh yeah, set security zones. Security zone WAN. No. ISP1. Host inbound traffic. System services ping. Edit security zones. And we do edit so that we can move a little bit throughout the tree. And we're going to copy security zone ISP1 to security zone ISP2. Set security zone ISP1 interface 000. Set security zone ISP2 interfaces 10. Ta-da! I'll commit that. Make sure all my other commits completed. Alright, so now from left, if we wanted to ping ISP1, we would go run ping 10.1.1.1. There we go. Alright, we haven't screwed up yet. The night is young. We've got plenty of time. Alright, 10.2.2.1, we are pinging there. Alright. Run ping 10.3.3.1. Alright. And 4.4.1. Alright, so we have left able to ping its ISP router, and we've got right able to ping its ISP routers. So now we said we wanted to get BGP up and running, so now we need to get BGP up and running. So BGP is a routing protocol intended to exchange routes. You can add a lot of different metrics, but we're going to keep it very, very simple. We're just going to get the BGP sessions established and then do some very basic route exchanges. We'll probably add a little bit of AS path prepending so that we can at least manage the paths a little bit, but we'll keep it very, very simple. So let's go back to left. And let's first start with our security zones. One thing you need to do with your security zones is you need to allow the BGP protocol. So we're going to go set security zone, ISP1, host inbound traffic, and it will be under protocols and BGP. And we need to do the same to ISP2. So we'll get that in there. And we're going to start with just left to ISP1. So we're going to go edit security zones. We're going to go show. So we're going to set security zone WAN, host inbound traffic, protocols, BGP, and we're going to go commits. So we've adjusted our security zones to allow BGP. Now we need to begin configuring BGP. So BGP is configured under the protocols, BGP. So first thing you'll want to do is you'll want to set a group, because that will make it much easier to manage multiple BGP configurations if you find that you have to. And in a scenario where you've got two different ISP routers, you may want to set up different BGP passwords so you don't accidentally establish a peering with the wrong ISP because you messed up your configuration. It's just one more step to make sure that you do it right and you don't have your traffic going in all kinds of wild directions. So we're going to go ahead and create a group, and we're just going to call this eBGP because we're going to be using external BGP, eBGP. We'll leave this one with a single group, and then we'll do right with two groups. So set group eBGP, and you can set the type to external. Within BGP, you'll also want to specify the family. So these will be the family of protocols that you're going to be advertising. And we're going to be doing IPv4, so we're going to do INET. And then you have different types of prefixes that you can advertise, and we're going to stick with unicast. So we're going to set group eBGP. And now that we've got these pieces set up, we're going to skip some of these other bits. If you had a more complex environment, you might use something like local AS, where you'll set your local AS for your autonomous system, for how you're going to be advertising your autonomous system to your peer. But we're not going to do that. What we will do is we're going to set our peer AS. Actually, let's go ahead and add our numbers. So for the left, we're going to go with 65,300. For the right, we're going to do 65,301. For the ISPs, we're going to do 7,200. No, we'll change it. There we go. 7,200 and 7,201. When you set up BGP sessions, there are a few things that have to line up. Both sides have to agree on the other's BGP autonomous system number. So if you're going to be establishing a session from left to ISP1, you need to make sure that your peer AS is set appropriately. So for this scenario, for this particular configuration, it'll be 7,200. And you will be setting your routers routing options. Top set routing options, and you have an autonomous system number option under routing options. So this will be a global autonomous system number, and we're going to set ours to 65,300. By setting it like this, it will apply to all of your BGP configurations implicitly rather than having an explicit configuration through something like your local AS configuration. So we set our peer AS. So now left is 65,300, right is 72, or not right, ISP1 is 7,200, so your peer AS 7,200. So next we need to set our actual peer. So group eBGP, and we will set neighbor, and we will set our neighbor's IP address. This also has to match, and I'll show you shortly here how to set that. Yeah, can I set that here? I think I'll have to have two different configurations. address of local end of BGP session. Okay, we'll try that. We'll see if that works. I haven't used that configuration yet. So first we need to do our local address. And for this session, it's going to be 10.1.1.2. Curious to find out if that's going to work.
Mm-hmm.
If not, I'll have to show you how we would do it differently. Actually, you'll see it on the right. 221. Local address is 10.2.2.2. So BGP is a TCP session. So your TCP session will be established from a specific address, and that is another piece of the criteria that needs to match for a BGP session to become the state called established. And established is a completed and usable BGP session. All right, so we've got our peers set. So we're going to go ahead and we're just going to commit this. So let's go commit check first. Let's make sure I got everything in here. Checking, checking, checking. Wait for it.
Come on.
There we go.
No whammies.
All right, we're going to... Yep, no whammies, no whammies. All right. So let's see where we were at. Yep, we got that. So let's go top. Let's go edit. Protocols, BGP. Group, Ebgp. So set type. External. Set peer. No. We're going to do all my BGP configs different, just for funsies. Family, inets, unicast. Set neighbor. 1, 2. Peer AS. So you can also specify your peer AS like this. In line with the neighbor configuration, and you'll see what that looks like in just a moment. So I will be able to put 2 neighbors in this single group by specifying the peer AS. Why would you want to do this? There's lots of different reasons. When you actually get your scenarios and your real world environments put together and you're trying to figure out how to organize as much of the config as you can to keep as many common configuration elements together, you'll figure out what most applies. The one important thing to know is that in this configuration, you will see that there is a hierarchy. So I could go and set peer AS here at this level, and at this level, peer AS 65200 would be overridden by peer AS 65300 because peer AS 65300 is closest to the neighbor. It is furthest down in the configuration tree, making it more specific rather than more generalized or global. So that type of configuration and what's the word I'm thinking of? That I don't know, precedence. That precedence configuration will always will apply throughout the configuration. The further from the root of the configuration tree you get, the greater precedence it has. So it will always override something applied higher up in the configuration. All right, so let's go set group, and we'll just go ahead and set the other neighbor. And that is 10.3.3.2, peer AS 65301, and local address is 10.3.3.1. All right. So before we change that, we're going to go run show, and we're going to show BGP, and we're going to do summary. So here you see we have our BGP configurations, and here are our 2 peers. currently they are both in a non-established state. So it is in active and it is in connect. Neither active nor connect are established, and as such, the session is not doing anything. So let's go ahead and let's commit this. Command, I believe, is refresh. Refresh in 2. So the command refresh in 2 will refresh or re-execute this command every 2 seconds. It's a great way to monitor progress. Give it a little bit.
What's an acceptable amount of time usually for something like that, Jeremy, to establish?
Oh, that varies. That varies. It's all dependent on what type of protocols or things you're trying to watch. Error in neighbor of group Ebgp. I know what I did forget though. No, not routing instances. Routing options. So set routing options. Autonomous system is 7200. I don't know if that's going to fix anything. So we shouldn't see any change over here. Still active and connect. Yep, there. That's what it was. So you always have to have your device's autonomous system specified somehow, either as a global configuration through the routing options or through the BGP configuration through the local AS configuration. So we specified it at the global level, and now our configuration checks and goes. Right. So let's see what we got. There we go.
Hey.
All right. So now we are established. So what we'll see here is iNet is the protocol that we're advertising into. So this is iNet or IPv4, and there are no prefixes being advertised. With Juniper's BGP configuration, and I don't necessarily believe this is 100% unique to Juniper, Juniper will not advertise any protocols via BGP that you have not explicitly specified or are already received BGP prefixes, and it will exchange those as appropriate. So what we need to do is we actually need to create a routing policy to specify which routes will be advertised. And what would we even be able to advertise? We can advertise this prefix. Or should we create a loopback? What do you think, Jared? Should we create a loopback?
Yeah, I think create a loopback.
All right, let's create a loopback. We're going to go top. So we're going to do a loopback. Loopback interfaces are fun. They're also very useful. You can use them for all kinds of wonderful things. They are typically used with routing protocols as a kind of anchor for establishing certain routing protocols or tunnels or other things like that. However, they do have kind of some limitations, but they are very useful for some operations. And you'll see once we get into the next video, which we're going to spin off of this one, which will be going into IPsec and some of the kind of overlay concepts, where a loopback would be exposed into the overlay network, and you can use that for reachability testing in a manner that's agnostic of the path, assuming that you can pass traffic. But that is typically how you will set up things with loopbacks. You would have a parallel IPsec tunnel configuration, and you're going to establish something like a GRE between the two devices, like between left and right. Or you're going to set up a BGP session within the overlay from left to right. But we'll get into that in the next video. So we've got our BGP up and running. So let's go ahead and create our loopback. So we're going to go interfaces, and the loopback is called LO0. And we're going to go unit 0. So you have to have a unit 0 if you're going to use a loopback. You can have additional units, but unit 0 is necessary. So we're going to go family inets, and we're going to do 1111 address 1111/32 because this is a host address. And we're not going to bother putting it into a security group because we just need to get that route into the table. So let's go ahead and do a commit, and let's see what it looks like in the route table. Loopbacks can be a lot of fun, and they can be very useful if you're going to be testing things like security policies or security zone configurations and other bits when you need to start exchanging packets and traffic within your devices or throughout your environment. Alright, so we're going to go run, show, and we're going to do route. So we're going to show our route table. Alright, so we see route 1111/32 is in our route table, and it is a direct protocol route. So we have a few other directs as well. So we've got a directly attached prefix for our segment between left and ISP1, and we've got a directly attached prefix for our traffic, for our session, for our link between left and ISP2. So direct is the protocol here. That'll be important next. So now we're going to go in and we're going to start creating our route policy. So we're going to go edit, and we're going to go policy options. And we have all kinds of policy options, but we're going to be doing policy statements. Then we're going to create a policy statement, and we're going to call it we'll go Ebgp, and what should we call it? Ebgp out. Let's call it Ebgp out. So you'll need two different policies when you start dealing with routing protocols and routing policies. You always need one for advertising out, and you'll need a policy for accepting prefixes in. And these are always going to be from the perspective of your route table. You are always going to be advertising from your route table, your INET0 route table, or whatever route table is appropriate. INET0 is what we're going to be dealing with for this situation, for this video. So we're going to be advertising out from INET0 via BGP protocol. So this is going to be out from our INET0 route table via BGP. So Ebgp out is what we're going to call it. All right, so we're going to go set, and we're going to create a term, and we're going to call this loopback. All right, and we're going to say from protocol direct, and we're going to go from interface LO0. Let's see if that works. and then we're going to go then accept, and then we're going to set then reject. All right, so here's what we've got. So we created a policy statement called Ebgp out. So Ebgp is the protocol, and out is the direction that this is going to be applied for all prefixes that are going to be advertised out via Ebgp. We created a term, and we just gave it an arbitrary name of loopback. This term is going to select routes from the table where protocol is direct and interface is LO0.0. When we look back at our route table, we see that there is a prefix in the route table that is protocol direct, and it is an interface LO00. So this should be advertised. So we are going to select all routes protocol direct where interface is LO00, and then we're going to accept that into this advertisement. It will be accepted by this policy for use in an export statement. Everything else is going to be rejected. This should be put into your routing policies. The reason is you only want to be advertising what you have explicitly stated. You should not be advertising with a very greedy policy. The reason for that is obviously if somebody puts something into the routing table, maybe you've got OSPF as well, and it's operating all kinds of additional routing protocols, or not routing protocols, routing prefixes. You don't want a scenario where you begin advertising the wrong prefixes out to your ISP for multiple reasons, and the least of which would be that it's just wasteful. You don't want to be exposing your internal network prefixes to your ISP because they don't need to know them. In the worst case scenario, your ISP could have appropriate security policies and procedures in place that when they see you advertising a prefix that they know you should not be advertising, they may shut down your BGP peering. And if they shut down your BGP peering, then you're not going to be receiving any prefixes from your ISP, and as such, you won't actually be able to route. So it's important to make sure that you've got an appropriate policy advertising only what you intend. If this were an internal network, or let's say maybe it's an MPLS network, and you're advertising prefixes in, they're probably going to be accepted. But you could create a routing loop where you could have traffic going in all kinds of wrong directions, or you could be creating a kind of split horizon or a bifurcated traffic pattern where you've got traffic that goes to your destination in one direction over one path and comes back to your source on a different path. Or you could even have a scenario where you've got traffic that's just going in the straight wrong direction. Maybe you've got a left 2, and the two of them are advertising the wrong prefixes. So left try to send traffic to right, but right has a bad prefix in its table, so it sends its traffic that it thinks is going back to left, but it sends it to left 2 instead because left 2 is advertising the same prefixes, and for whatever reason, it is taking preference. So always make sure that you've got good policies that are clean and explicit. So there's our policy.
Nice. I can remember I'd get hung up every time I did this. It took me a while to wrap my head around then accept, then reject. It almost seemed like you were, I don't want to say countering what you just did. It's just because of where it falls in the tree, correct? I mean, because you're accepting from that interface, but then rejecting all others, right?
Correct. Rejecting all others. So this is more of like a fall through list kind of function, where this would be that implicit deny at the end of the list.
Sure.
So this will take precedence. It will be accepted. And then once it's accepted, there's no further processing of that route from the table, and it moves on to the next route in the table. It will always operate in that fashion. So this policy is going to go through your route table one prefix at a time, and it will accept and accept and accept and keep shorting through all of your prefixes. If it's not accepted, then it will be rejected. It goes through very, very, very quickly.
Perfect.
All right. So we've done that. Let's go up, and let's go ahead and let's create an Ebgp in policy. And we're going to go set term, and we're going to call it from Ebgp, and we're going to go from protocol BGP, and we're going to go then accept, and just because we're going to keep it consistent, reject. There we go. Very simple. So let's go top, edit protocols, BGP, group Ebgp. All right. So now we're going to set, and we're going to go export. So we're going to tell it which export policy to use. And we're going to call Ebgp out. And we're going to set import Ebgp in. There we go. All right. So now we're going to go commit. All right. So that's how you advertise protocols. That's how you advertise routes into a protocol. Now, with ISP1, we're not going to create any export or import policies. With BGP and the Juniper configurations, they have an implicit import from the protocol into the route table. They have an explicit export of all from protocol. So it will always export BGP learned protocol or learned prefixes. It will always import BGP learned prefixes, but it will not export something that is not already in the BGP tables. So let's go run show BGP summary, and we'll show you in just a moment. Oh, it didn't work. Our policy didn't work. Shoots. All right, so let's go ahead and fix that. So policy options, policy statements, Ebgp out. All right, so we're going to delete term loopback from interface L00. And let's do this. Let's go set term loopback from looking for filters. Nope, that's not what I wanted to do. Set term loopback and from let's go with route filter. Let's go with this address mask. I don't think I want that. We're just going to go 111/32. Exact. All right. So that should work.
So, what, Jeremy, what's your guess as to why the other one didn't work? Because I would have honestly half expected it to work.
I don't know. I'm gonna have to take a little bit deeper dive into that one.
Matter of fact, I feel like I have done that.
I
And
feel
it
like I have
worked.
too. Maybe I'm screwing something else up here. Or am I doing this wrong? Let's do this. Let's go roll back one. I think I might be missing something here. We're going to commit. It might not be showing advertised my advertised prefixes. Let's go. Let's make this bigger. So this is only showing the prefixes I'm receiving. So let's go run show route advertising protocol BGP, and we have to do the neighbor, which is 10.1.1.2. Nope, 10.1.1.1. All right, so it did work. All right. So there you go. That's how you look at the prefixes that you're advertising. You have to go through the advertising protocol for the specific protocol, and you have to have the neighbor. All right, so now if we go here, we should be able to go run show route, and we see 11132. We see that it's learned from BGP, and here is the autonomous system path. So 65300 is where it originated, and this tells you how to get to it. So we're going to go to the next hop router is 10.1.1.2, and that is via the GE000.0 interface. So let's go back over here. All right, so we see our loopback has been advertised, and that is good. Let's go to our rights, and let's go ahead and get this one set up. So show security, show. All right, let's go. Can I do a wildcard set? Let's set. That's system services. Yeah, we'll do it like that anyways. Yep. All right, so we did our wildcard set for range, and since we named our two security zones with a pretty good naming convention, ISP-1 and ISP-2, we are able to use the wildcard range. So I use the square braces here, the square brackets, and we did 1-2, so for all numbers between 1 and 2, and we added the protocol BGP. So there we go. So that's set up. Let's go top. Let's set routing options, autonomous system number 65301. And we're going to go edit protocols, BGP, group, eBGP. Let's do separate ones. Group, ISP1. And we're going to set type external, set peer AS, 7200. We're going to set family INET, unicast. We're going to set neighbor 10331. Peer AS. No, we don't need peer AS. Local address is 10332. We're going to copy group ISP1 to group ISP2. Edit group ISP2. Show. 2. And we're going to go into our routing options and policy statement, not routing options, policy options. ISP1, Ebgp, out. That term, loopback from protocol direct, interface LO0. Then accept. Then reject. Go up, set policy statements, and we'll just do one for all. From BGP, from BGP, from protocol BGP. Then accept. Reject. All right, we're going to copy policy statement, ISP1 to policy statement, ISP2, Ebgp out. All right. Edit protocols BGP group ISP1, and we'll go up set group ISP1 export ISP1 Ebgp out, import Ebgp in. There we go. All right, so we've got our policies applied. We've got our two ISP1 and ISP2 Ebgp outs. So the two policies are exactly the same, but maybe in a later, at a later time, I'll choose to do something different, and maybe I will advertise differently to ISP2 versus ISP1. So I have two separate routing policies now for how I'm going to manage my advertisements. It's good to have multiple policies if there's a reasonable expectation that you're going to need them. So don't create more policies than you need, because they can become a lot and they can become very unwieldy and complicated to manage. So try to keep it simple as much as possible, but don't let simplicity hamper your designs. Don't let simplicity limit your capabilities. So let's go ahead and commit check. Oh, I know what we forgot to do. We're trying to advertise a loopback prefix. We don't even have a loopback interface created. Let's go ahead and put these numbers on here, by the way. Always try to keep track of your numbers. If you've got an IPAM, use an IPAM. If you're too lazy to set up an IPAM, then I guess set up a spreadsheet. I hate using spreadsheets for IP address management.
I would agree. So let me ask you a question, Jeremy. With your policies, like you said there, with the keeping it simplistic but don't essentially box yourself in, will you typically set something at a minimum so that you can grow if you need to, or will you make it simple and then if you ever have to grow it, then just change it at that point for simplicity's sake? Just in a personal opinion.
I would take it, with it depends kind of answer. If I have no expectation that I'm going to be treating my two ISPs or my two BGP peerings differently, then I will probably keep a single policy. But if I have the reasonable expectation that within at least a brief period of time or within a foreseeable period of time I would want to be handling my two connections differently, then I would just go ahead and create the two policies, even if they're the exact same, but I would put them in place so that I can recognize and with minimal change modify one of the policies. So it all depends on the level of effort, how big your policies are, those kinds of things. There's no reason you couldn't create one and then change your mind later and create two. It will cause some routing issues. When you change the policies, you might have some prefixes that are going to be withdrawn and then re-advertised, reinserted for no obvious reason, just because you change policies. But
Sure.
it's not a huge deal. Policy or prefix withdrawals and reinsertions, might take a few seconds, but it's not a huge deal. The bigger concern will be whether or not you actually did everything correct. Anytime you start changing something so significant as an export or import routing policies, you run a lot of risk of, did I fat finger a number? Did I forget something? Is there something that's just not right that's going to cause a significant issue or fail to bring in all of the necessary prefixes? This can be very important, especially if you're remote managing a site. And the prefixes are going to be coming in via this policy, the ones that you would be using to get to that site. If you do screw that part up, then the site will be down for a period of time until the config rolls back, assuming that you did a commit confirmed, or it's down hard for an extended period of time and until somebody can get a laptop or something to SSH into the device because you chose not to use a commit confirmed. So this would be one of those scenarios where commit confirmed is going to save you from any potential mistake, and always try to use commit confirmed. Nobody expects to make mistakes. They're always unexpected, so be prepared, be smart, be responsible, use commit confirmed.
Sure. Perfect. Thank you.
I got my headphones cable all wrapped up again. All right. So let's commit this. Oh, you distracted me, man. I forgot I still got to create the loopback.
I was gonna say you didn't create the loop back.
Man.
I'm trying to create the realistic environment where you have the coworker who comes over to your cubicle and interrupts you while you're programming.
Yep, there you go. That is the real world, man.
Oh, absolutely it is.
So in those scenarios, it's always good to use your show compare as well. If you get distracted by something, just to see where you're at and making sure that you're ready to make this commit and you're not, trying to commit a half-baked config. So we'll see that in just a moment here. All right, so we'll go show compare. So just to make sure I know what I'm actually going to be trying to commit here, so I've got my loopback, I've added an address, and we're going to go ahead and commit that. So show compare is a wonderful tool. I strongly recommend that you get very familiar and comfortable with it. Committing. And we're going to do this. We're going to go run show route because we know what prefix we want to see. And we're going to go refresh to. So when you do run show route and you actually supply a prefix, it will check all of your route tables for that prefix and show you any of the matches for that.
Oh.
So there you go. So now it shows us that in inet0 table, we have 2222/32. We see that's coming in via BGP. And we see that the AS path is 7200. So that's the nearest hop. And here is the origin, which is 65301. And this is where it's coming through.
Nice. I didn't even know that existed.
Yeah. So it's very good, and it's a wonderful tool, especially if you've got giant route tables or you've got lots and lots of routing instances. So that will help you find the route that your traffic might be taking, depending on what you've got going on. If it's a routing instance or if it's the default routing instance, this will help you find all the possible paths that your traffic could be taking. If it didn't match as a 22232, it would match at the next most appropriate route. So if you had a 000/0 route in your table, it would show you this route table with 000/0 as the matching route for that prefix.
Okay.
And then, obviously that tells you something, right? That tells you
Sure.
that where you were expecting this host route that's advertised via BGP, it's not there, and it's taking a default route, and that might be via a different interface. So that results in obviously your traffic going in the wrong direction. Also, in a real world scenario, if you're actually out there configuring devices, don't use 1111 and 2222. Those are real prefixes out on the internet. Always try to use bogons, the RFC 1918 prefixes, your private IP spaces, your 10s, your 172.16, those types of prefixes, 192.168. I'm just using these because they're easy to remember. All right, so our prefix is there. So now what we will not be able to do is ping yet. Well, we can't ping that for multiple reasons. What's one reason I wouldn't be able to ping that, Jared?
Let's see. You're trying to ping. You're in left, trying to ping over there. Well, you don't have. Well, it's going to say no route to host, right? Because. Well,
No,
no, you're not
sir.
getting that right now.
No, because I've got a route. It's right there.
Yeah, you do have a route. Let's see.
But that is a good point.
Oh,
If I did not have a route that matched in the table, it would tell me no
sure,
route to
it
host.
would say no route to host. Let me think here. Pinging. Where are you getting anything back?
So where would you begin troubleshooting that?
Well, you don't have a route to 1.1.1, right? You don't have a route back.
Let's check. So from right to left, do we have a return route?
Correct.
So let's go run show route 111.132.
Well, you do.
So we're trying to send a ping from left, and we're going to go across ISP over to right.
Which the packet is, it has a route and it's gone. But you are not getting anything in return.
Correct. We are not getting anything in return. That is the correct statement. You are absolutely correct on that. That is a valid assessment. You didn't put in any assumptions, which is good. We're not making assumptions as to whether or not right is receiving that echo request. But all we do know is that left is not receiving an echo reply.
Correct.
So in a real world scenario, you would not be able to manage your ISP. But in this
Sure.
scenario, we are able to manage our ISP. If you were operating your own network, let's say you had some leased lines, some point-to-point circuits, and you had a transit router somewhere within your network, your next bet would be to determine whether or not you can reach your next hop router. So first we're going to go run, and we're going to ping, and we're going to ping 10.1.1.1, and we determine, yes, we can ping it. We've got 222 over here, but we don't have 10.3.3.0 in our route table, right? So let's go run show route 10.3.3.1/32. So that is not in our route table, and that's fine. That's fine. No big deal. We should probably have that in our route table. So we're going to go ahead and we're going to advertise that one. So we're going to go top, and we're going to go edit policy options, and then we'll return to the troubleshooting part. So stick with me for a second here.
Okay.
Policy statements, and we're going to go Ebgp out. And we're going to set term, and we're going to call it from direct. And we're going to go from protocol direct, then accept, then oops, we need from protocol direct and BGP. All right, and we'll look at that in just a moment. All right, so in our Ebgp out, if you do not specify an export policy, there will be an implicit export. That implicit export will be to export all BGP learned prefixes. If you create a policy and you make an explicit export statement, if you do not have a from protocol BGP or something to that effect, you will not be advertising out prefixes you learned from BGP, because there is no longer an implicit export policy. So we had to make sure that we did a from protocol BGP. Now obviously our term name is not correct, and you'd want to fix this because now it's all sloppy. But we're gonna leave it because it's quite honestly I'm a lazy engineer. So Ebgp, and we're going to go export, and we're going to go Ebgp out. All right. So now what did I do? So here's direct. Here's BGP. Well, there's the route. Huh. All right. So specifying the prefix does a far more specific match. Without the prefix, it matches the IP address. All right. So now in our route table, we see 10331. So now we can keep going hop by hop. So from left to 10111, we were able to ping. So let's see if we can ping the other side of ISP1. So that would be 10331. So run ping 10331. All right, so we cannot ping 10331. So that means that something is happening between left and ISP1's far side interface from left. So here is our near side interface. Here is our far side interface. So let's look at ISP1 and let's see what its far side interface configuration and other bits look like. So in this scenario, since these are SRXs and they are security first, I would start with checking your security zones. So let's go show security zones and let's see what our security zones look like. So we've got one security zone named WAN and it is accepting ping and it has two interfaces in it, GE000 and GE001. So if we show our interfaces, we see GE00 and we see GE001. 001 has 10331 interface address. That's what we're trying to hit. So let's go ahead and now we need to check our security policies. And we don't have a security policy. With the SRXs, there is no implicit security policies for any named zones. So for security zone WAN, for traffic that is going to be going from WAN to WAN, there is no policy. So we need to go edit security policies from zone WAN to zone WAN. And we're going to set policy. And we're going to call this policy permit ICMP. And we're going to go match source address any, destination address any, and protocol, application, and Junos ping. All right. Now, with all of that put in, we're going to go then permits. All right. So now we've got a policy rule that permits ICMP, application Junos ping, permits, and it is applied to the from zone WAN to zone WAN. So we're going to go top and we're going to go permits.
You know, I completely forgot that even when you are just sitting in the zone for two interfaces, that you would still have to create that policy.
Yes, sir. There is no implicit allow, even if they're in the same zone. There you go. So now traffic is pinging between left and the far side interface of ISP1. So we know that we're able to at least cross ISP1. So that is step one. So let's try the next interface, the next hop on our path. So 10332. So we ping that, and we're able to ping that. So now our final test, run ping 2222, and no dice.
Still no dice.
Still no dice. So now we need to go a little bit further. And we need to check out what's happening in write because we know that we were able to get all the way to .2 and we were able to get a response. So let's go back to write. Oh, no, that's ISP2. So again, same thing. Let's check our interfaces just to get an idea of the lay of the land here. So here's 2222 and it is on loopback 0. All right, so let's check our security zones. So we see ISP1, and here's our interface. And we see ISP2, and here's our interface. What we don't see is our loopback. We don't see our loopback on here, do we?
Yeah. No security
so let's
zone.
go set security zone. We're going to call it trust. Trust, host inbound, system services ping. Interfaces LO00. All right, so now we've got a security zone. But our traffic...
I have a policy, right, between ISP1
Exactly. So we need a policy since our traffic is going to be coming in on ISP1, and it's going to be going to the interface LO0, and it is going to be going to trust. We need to go edit security policies from zone ISP1 to zone trust. So we're going to set policy, and we're going to call it the same. Permit ICMP, match, source address any, destination address any, and application. Go ahead.
Now, if I'm thinking about this right, you'll also have to create one between trust and ISP1, correct? Otherwise, you won't get a return ping. It won't go back.
It's a good question. Why don't we find out? All right, so we created a match, but we obviously forgot our then. So we're going to set policy, permit ICMP, then permits. And we're going to go commit. All right, let's see what we got. Let's wait for this to finish committing, and then we'll go back. It'll be a surprise. We'll be all excited. All right, here we go.
Oh, look at that.
Why do you think that is? So the reason we're able to get this,
I half expected that there'd have to be another policy. To be honest with you.
Yeah, and you would be right, but not specifically in this scenario. And I'll show you where that scenario is applicable. In this scenario, we are pinging 2222, and we are going to your Juniper device will always source the traffic from the interface nearest the destination according to the route table. So when left is checking the route table to reach 2222, it sees that it needs to go via GE000.0. So it is going to specify that interface as the source for the packet. So it's going to be going out this security zone, traversing across here, entering into this interface, the security zone, then going into the loopback. Security zones, security policies are stateful packet filters. So where you can get traffic in, traffic can go back out through the same permitted state. So in this scenario, it would be permitted bidirectionally if established through ISP1 toward trust.
Okay.
The scenario that you're referring to would be if I did this and specified my source as 1111. In this scenario, it should not be permitted, but it is. And this is a different. This is a special case, and it's more complicated.
It's a rabbit hole.
Not necessarily a rabbit hole, but it gets a little bit deeper. And this is where you get into more of the advanced filtering. So this traffic is being sourced from a different zone called Junos-host. And Junos host does have certain privileges. And one of those in this scenario is that it doesn't have to deal with the limitation of this specific scenario where I don't have a policy. So if I go to show security zones, I don't even know if I have this loopback interface. Yep. So this loopback interface is not specified here. It's part of Junos host, and it is allowing me to source this traffic.
And
But
is Junos host the one thing that it's like an implicit allow instead of an implicit deny? Is that right?
kinda.
Okay. So
In some cases, it is. For inbound traffic, this is the filtering. This is the first line filtering for that Junos host policy. There
okay.
are a lot more details specific to Junos host that make it a little bit more complicated, but when you start talking about how you start managing more of the traffic coming in, let's say I wanted to only allow write um, ISP1 interface, this one right here, 10331, I would have to use a Junos host policy so that I could filter by that IP address. First, I would need to accept ping in for host inbound traffic on this security zone. Then I would have to have an additional policy for ISP1 to zone Junos host where I could then apply additional filters. So this will be the first line filter allowing all ping, and then I would have another policy that would filter the permitted ping traffic. So I
Mm,
could then say only 10332 can ping my host. This is a very important policy for anybody who's going to be creating a SRX configuration for a device that's going to be internet exposed. It is very important to understand what the Junos host policy does and how to use it properly, especially if you're going to be remote administering a site. If you're going to be allowing SSH into your Juniper SRX, always filter that SSH traffic inbound to your SRX through a Junos host policy, filtering on that source IP address. So if left is going to allow right to SSH into it directly, left should filter by right's source address, which would be this
okay.
10332.
Sure.
If you do not filter that, you will find yourself in a scenario where you are getting a whole bunch of worthless, garbage SSH sessions inbound to your device, which can expose you for compromise. So definitely filter that. At the very least, you'll be getting useless traffic that's going to start potentially bogging down your device and consuming resources on your SRX that would otherwise be used for actually passing traffic. So it's important. We had a device in one of the installs that I did that we did not filter the SSH properly, and we had all kinds of garbage coming into it, and it was actually preventing the device from responding uh, reliably. It was getting very, very poor performance, extremely high latency. Once we locked down the Junos host configuration a bit tighter, a lot of that garbage went away and the device became responsive and significantly higher performance again. So, Junos host, definitely use it. And we'll look at that a little bit further probably in our next video, because we're already at an hour and a half here. So let's quick knock this out and let's get this done. So left, we're going to have to create a policy for left if we're going to allow right to ping back into it. So let's go show security zones. So edit security zone trust, set host inbound, system services ping, set interfaces LO00. Up, edit, up one more. Edit policies from zone ISP1 to zone trust. Set policy permit ICMP match source address any destination address any application Junos ping. Now my backspace, then permit. Then we go up, we go show, and we like, oh yay! And we're gonna go copy from zone ISP1 to zone trust. to from zone ISP2 to zone trust. There we go. Now we've got 2. Up and show. All right, so we've got 2 zones, ISP1 and ISP2, and we've got a 3rd zone, trust. We created a policies, ISP1 to trust and ISP2 to trust. So now we have 2 policies that permit traffic, and we're going to go commits. We're going to go back over here. We're going to go run ping 1111. There we go. All right. So we're going to go to here, and we're going to go show. What are we going to do? No, we don't want to do 1. We're going to go to 2. All right, so we've got 2. Let's just check out what our security zones look like. All right, we've got 1. So let's go set routing options. Autonomous system is 7201. We're going to go edit protocols, BGP, group, Ebgp, set type external, set family inet unicast, set export Ebgp out, set neighbor 10222 pure AS 65300 local address 10221 set neighbor 10442 pure AS 65301 local address 10441. Yes. All right, so we create an export policy or reference here to a export policy that does not exist, which is fine because we're going to go set that now. So edit policy options, policy statement, Ebgp out. And we're going to set term from direct from protocol, and we're going to go direct BGP. Set term from direct, then accept, then eject. All right. And edit security zones, show. We need to make sure that we set our security zone, host inbound security zone, WAN, host inbound, protocols, BGP. All right. Now we need to go up and we're going to go edit policies. And we're going to go edit from zone WAN to zone WAN. And we're going to set policy permit all, match source address any, destination address any, application any, backspaces, then permits, and we're going to commit check. Checking. All right, we succeeded, and let's go commit. And we're going to go run show BGP summary, refresh 2. Oops. So I can already see that we're going to have an issue here. So you see we've got this set up here. 10221, and I've defined its AS as 7200. So let's go edit protocols BGP, show. Alright, so you see we have pure AS 7200. So here's a wonderful example of what we're talking about with configuration precedence. So neighbor 10221 pure AS 7201. Let's go run show BGP summary. There we go. So now you see that it changed to 7201 and we are established. We're also receiving some prefixes. And let's see what we're advertising. Run show route, advertising protocol, BGP, and our neighbor is 10221. There we go. Very good. So we see that we are still active on this peer. So let's go ahead and let's see what we got going on over there. Let's start with our protocols. Well, there we go. We did it again. See, our pure AS is 7200. So set protocols, BGP, group ISP2, pure AS 7201. We're going to set it refresh so we can watch it. And there we go.
There it is.
There it is. So we now have the BGP sessions all established and everything is looking good. What we unfortunately do have is a scenario of equal cost paths. And this will be an issue with the SRX devices. It may not be an issue today. It may not be an issue tomorrow, but it will eventually become a scenario where you have a path such that left will go through ISP1 to right, and ISP1's return traffic will go through ISP2. In this scenario, you have an issue where the forward path and the reverse path don't match, and you will have a scenario where the states don't match. Since you created an accepted path, an accepted state out, it will not accept traffic coming from right into a new interface. That will appear as a new attempted state that will be unsolicited inbound traffic, and if there is not a matching policy that would permit that, then that would be denied traffic. Even if it were permitted inbound, since the two paths are going in different ways, if this were a TCP session, it would be dropped shortly after the states are created because it doesn't see all of the appropriate TCP handshakes completed in the same state designation. So the left established through 00 interface and the return traffic to complete that TCP handshake will not exist, and this state will no longer be valid. This state that was created coming from right in would not be valid either because it wasn't properly established. So both states would be terminated. So if you had a short-lived timer such as like 10 seconds, You would have a TCP session that would hold for about 10 seconds, and then it would be terminated. And then a new one would have to be established and terminated 10 seconds later. This becomes a significant problem. What you would have to do in this scenario is set a situation where ISP1 is your preferred path, an active path, and this would be your secondary path. So then what you're going to do is you're going to set one path to be less preferred. And we'll go ahead and we'll quick knock that out, and then we'll call this stream complete for this bit here. And then we'll continue into part 2 later. So to do that, what you have to do is set one of the paths to be less preferred. I call that shaming. So you're going to shame this path. You're going to set it to a lower preferred path. How you do that is by advertising out that this path is less preferred. You do that through what they call AS path prepending. And that's how you manipulate your ingress traffic.
That's the key. I always thought about it the other way.
BGP exports are always telling the world how to reach you. Telling the world that you are a router for this prefix. And you tell the world what your AS path looks like when it is originated. And one of the path selection mechanisms for BGP is AS path length. So when we went run show route, we could see that for the 222, here is the AS path, and it has a length of 2. So we have the transit router and we have the originator. So what we're going to do is we're going to go into our policy options and our policy statement. Do we only have one? Yes, we do. So we're going to go edit policy options, and we're going to copy Ebgp policy statement, Ebgp out to policy statement, Ebgp out secondary. And we're going to edit policy statement, Ebgp out secondary. All right, so through our secondary, we have this. So what we're going to do is we're going to set term loopback then, and we are going to do an AS path prepend. And in our AS path prepend, we're going to prepend AS numbers to an AS path. And what we're going to prepend is 65300, 65300. So we're going to add 2. All right. There we go. So we're going to add 2 65300s. So we're going to go commits. No, we're not. We need to actually apply this export policy, don't we? Edit protocols BGP, group, and eBGP. All right, and this is going to be peer 10221. So we're going to set neighbor 10221, export eBGP out secondary. There we go. So now again we see this configuration where we have configuration further down in the config tree. This one's going to be specifically under this neighbor, so this will take precedence over this and this. So we're going to go top, and we're going to go commits. So remember that we are shaming the connection. We are telling this prefix, this advertisement is less preferred than the other. You don't tell the world which one is your preferred path. You tell it which one is not preferred. So now if we go run show route advertising protocol BGP and our neighbor of 10221, we see 1111, and our AS path is 65300, 65300, 65300. So this is a much longer AS path now. So if we go over to write, and we're going to do the same thing on write. So let's go show protocols, BGP. So this is one of those scenarios where from out the gate, from the start, we had a different export policy. We have this export policy. So we're going to go edit policy options, policy statement. There we go. And we're going to set term, loopback, then AS path prepend, and 65301, 65301. And then top and commits. So let's see, run show route 10 2222. There. All right, so now when we look at our prefix as being advertised from right, we see that we have two possible paths, this one being active, and this one is active because the AS path is significantly shorter. The longer AS path going via GE001 is not preferred because it is a longer AS path. Now when we look at write, run show route 1111, we see a similar configuration where this is the shorter AS path going via 0. This is the longer AS path going via 1. Now, with this explicit configuration, with this AS path prepending, we know that as long as this path is active, more specifically, as long as this and this BGP neighbors, these BGP peerings are active and prefixes are being advertised, that path will always be preferred over this one bidirectionally, since they both match the same path going to 2222 and going to 1111. As long as this path is active, then all is well.
So, quick question. Obviously, you can see there what your preferred route is or what route it is currently taking. Is there something that you can run to confirm it, that that is definitely taking that path, or is this the only thing you have is viewing that to that address, that is the path that is, so we got a trace route.
Yeah, you could do a trace route. However, trace route uses a UDP packet to make its path, so this isn't going to come out and give you very much good information if it's going to succeed at all. So without allowing a trace route, chances are likely you're not going to have a tool like that. As far as determining the path, just making sure that when you look at the two routers, so we are in left now, so trace route isn't working, which isn't an entirely unexpected thing. One thing that you should note when you're getting into an environment and you're beginning to do troubleshooting, always challenge your assumptions about what is a known good or bad states. If you go into a situation and you begin trying to use traceroute, and traceroute is not succeeding like it is here, don't jump to the conclusion that there is an issue with the path just because traceroute isn't working. If you don't know that traceroute being successful is a known good state, then don't allow that information to be part of your troubleshooting facts, if you will. Only accept facts that you know to be true. Some environments won't allow ping at all. So using ping um, as a path verification or host reachability troubleshooting step isn't valid and doesn't work. So make sure you understand what the known good states are. What you could do in a scenario like this where you want to make sure that you've got matching paths is look at your AS path. So from left to right, we've got 7200 and 65301, where 65301 is the originator. If we look at right, we see 7200 is still the AS that is next hop, which is good, and 65300 being the originator, and the path is the same length. So with this information, we at least know that the path is somewhat equivalent in that the next hop routers for both sides are of the same autonomous system. That doesn't necessarily mean that this path is optimal or that this path is correct or working, but it's got a significantly higher probability than if you had an entirely different autonomous system. Your bigger ISPs are typically going to have the exact same autonomous system end to end, so you won't really have an issue of different autonomous systems left and right if you've got the same internet service providers on each side. If you had multiple internet service providers, let's say you've got Verizon on the left and you've got Lumen on the right, you would see Verizon's autonomous system and you would see Lumen's autonomous system in both of the paths advertised to both the left and the right. They may have different routers in between since this is the internet, but it's one way to determine. Traceroute is, of course, going to be one of your easiest tools if you can get it to work. So there you go. That is a 4-router configuration illustrating a dual ISP architecture between two different routers, let's say within your administrative domain. We set up BGP, we set up path failover. So in this scenario with the two BGP peerings that each of the routers has, and the AS path manipulation that we performed, the AS path prepending, we now have a failover path configuration where if ISP1 fails, like it, no, we don't want to kill all of them. So when ISP1 fails like this, and left is still trying to talk to right, make me type it again. It will be able to talk to right still. One, in a failover scenario like this, BGP by default has pretty long timers on it, so it'll be, I think it's 30 seconds before it withdraws stale prefixes. So we will have to wait a period of time before all of the prefixes are pulled, withdrawn from the table, and an alternative path is computed. So we established this failover configuration with two ISPs, which is a very common larger enterprise type of connectivity solution, and it's going to become more and more necessary and popular as the world gets more involved in networking, and the necessity of connectivity continues to grow and increase, and cloud services become more and more popular and of value. Did we forget to create a policy? No. We've got the right one there. Eh. So we forgot to create a policy. So we're going to copy from zone ISP1 to zone trust to from zone ISP2 to zone trust. So had we configured our devices properly, it would have failed over successfully. But this is a very good reason that if you are in an environment where you do have a failover configuration capable, you should test your
You should
failover and
test it, right?
failback mechanisms. What's that?
Yeah, you should test, right? I mean, if you have
Yes,
the
you should test that.
capability.
It does, of course, require you to actually either go in after hours or schedule a maintenance window or something to that effect, but you should know that your failover mechanisms do work. If you aren't able to test your failover mechanisms, then you cannot operate with the assumption that they will work when you need them to. So do test your failover mechanisms. Same with your backups. Test your backups. If you don't test your backups, then you'll never know if they actually succeeded or they're going to work when you need them. And then you're going to get hit with ransomware. Everything's going to be encrypted. And you're going to be explaining to your executives in the C-suite why all the data is gone and you can't recover it from the backups that they've spent thousands of dollars on hardware to implement and support. So test your backups, test your failover. That's a good idea. You won't regret it. So we have a failover, routing, everything's good. In our next video, we're going to start talking about overlay networking. The concept of overlay networking is newish in terms of networking. Networking is a very slow to move, slow to adopt new concepts because of its criticality in everything IT. The industry is very risk averse, so they don't move very quickly to new technologies or adopting new architectures. So overlay networking is what is the term used for your IPsec VPNs and other VPNing technologies where tunnels are being established in a more complex configuration. If you're just establishing a site-to-site VPN and doing nothing exciting or interesting with it, it's not typically coined an overlay network per se. But if you're going to begin using it to build GREs over and other more complex structures and technologies, then it gets coined an overlay architecture. But for the sake of our next video, we're going to stick with the term of overlays because it's more ubiquitous with everything else that's trending right now in the networking spaces with microservices, Kubernetes, large clusters, and other bits. So we'll be building some IPsec tunnels between left and right via ISP1 and another one between ISP2 across ISP2. We're going to set them up in a parallel configuration so that you have two tunnels that are operating concurrently. And that'll allow you to do other things like automatically testing and making sure that your failover solution is likely to work and that your paths between left and right are going to succeed. And we'll begin talking about what other bigger overlay architectures there are out there, like VXLAN or MPLS or L3 VPNs, or even something like source packet forwarding or Spring or segment routing, and talk about traffic engineering and other bigger technologies that you might implement in a significantly larger enterprise where you need more segmentation or more traffic management. So thank you for watching, and we look forward to seeing you in our next video. If you enjoyed the video, like and subscribe, leave a comment, tell us how we're doing, any suggestions for our next videos. It's very appreciated. Thank you.
Thank you.